everybody get the file that I sent?
Yeah.
Good. Good. All right. How's everybody doing? We're going to see how this works. I'm running things through my hotspot, and so they don't have fixed internet at home, so we'll see how this goes. Hopefully this is clearer than what I was trying to do with the projector the other day. Like I said, hopefully everything works. If it doesn't work, if something happens, if you think this really sucks, let me know. We'll have to try to do something different. But we'll see how this goes today. Sound like a plan?
Yep.
All right. So to get the double angle formulas, we need to go back and remember what our sum and difference formula, basically the sum formulas, were for the different trig functions for sine, cosine, and tangent. So just to remind off to the side here, remember your sine of alpha plus beta was sine alpha cosine beta plus sine beta cosine alpha. So when we do the double angle formula for sine, we're going to use the sum formula to help us figure out what this is, and then do some simplifying. So the way we get at this is that we rewrite 2x as just x plus x. Being very, very clever there. So then we can use x as alpha and x as beta. So when we use that, we get sine of alpha, but just that'd be sine of x, and then cosine of beta is going to be cosine of x. And then the same thing the other way around, because alpha and beta are the same thing. So then we get sine of x, cosine of x, which means we just have 2 sine x cosine x. So this, what I'm going to box here, is your double angle formula for sine. Not too bad of a derivation to do, especially if we remember what the sum formula is for sine. We can do something similar for tangent, but we have to do the same idea. We have to remember, I'm going to write this one a little bit lower because it leaves me a little bit more room. We have to remember what our sum formula for tangent was. Remember, tangent is tangent of alpha plus tangent of beta over 1 minus tangent alpha times tangent beta. Remember that when we had the sum formula for tangent, it was still a sum on top, but the sign flipped on bottom. Okay. But we're going to do the same trick for tangent that we did for sine, and we're going to do the same trick when we get to it for cosine. We're going to rewrite 2x as x plus x. And then same idea here. We recognize we're going to plug in the x for alpha and the x for beta. When we do that, we'll get tangent x plus tangent x on top. And on bottom, we'll get 1 minus tangent x times tangent x. And then if we simplify, I've got tangent plus the tangent x plus tangent x on top, so I get 2 tangent x on top. And on bottom, I've got tangent x times tangent x there, so I'll get 1 minus tangent squared x on bottom. So I'll box that one in too. So there's our double angle formula for tangent. We're going to do an example here with each of these in a minute. I want to go ahead and get these formulas down so that we can use them. Are there questions on how I got either of those two formulas? Again, the sum formulas are ones that we already knew, right? We okay with those?
Yeah.
Cool. All right. So, turns out, I mean, they're all important, but it turns out that the cosine of 2x one is the one that actually gets the most use later on in applications, especially in calculus. So that's why I've got 3 equal signs next to that one. Let me go just remind again here at the bottom. We're going to do the same kind of thing that we did for sine and cosine. I want to first remind what the sum formula for cosine looks like. Remember, it was cosine alpha, cosine beta, and then minus sine alpha, sine beta. So doing the same thing that we did before, I'm going to rewrite 2x as x plus x. And then again, treat your x as alpha and your x as beta. So you get cosine x times cosine x, then minus sine x times sine x, which then we can rewrite as, oops, this should be 2x. Sorry about that. So rewriting that, we get cosine squared x minus sine squared x. So here's one of the formulas. But again, like I said, I had 3 equal signs put down here on this particular double angle formula, because we also know a couple of things that we can plug in for each of these. We remember one of our Pythagorean identities was sine squared x plus cosine squared x is equal to 1. So one of the first things that we could do is solve this for sine squared x. And you get sine squared x is equal to 1 minus cosine squared x. And we could plug this in to our identities that we just found. We could get that our cosine of 2x is also equal to cosine squared x minus 1 minus cosine squared x. Distribute that negative sign through. So you get cosine squared x minus 1 plus cosine squared x, or get to 2 cosine squared x minus 1. Okay, so that's another way to write cosine of 2x. These two things are equivalent. All we did was plug in 1 minus cosine squared for sine squared and simplified. But notice that I chose to substitute something in for sine squared. I could have just as easily, using the same Pythagorean identity down here, I could have chosen to plug in 1 minus sine squared for cosine squared. Could have just as easily done it that way as well. So if I go back up to the first one, we would have cosine of 2x is equal to 1 minus sine squared x minus sine squared x, or cosine of 2x is equal to 1 minus 2 sine squared x. So we have 3 different ways that we can rewrite cosine of 2x. Now later on, when we do half angle formulas, these will become important. And when we do solving some trig equation stuff later on, these will become important. Okay, so it's important to know all 3 of these. One of the reasons why we want to know these 2, the second 2, is because notice that when we replace this cosine of 2x with something, we don't have any signs in it at all. Notice this one, if we replace this cosine of 2x with this, we don't have any cosines in it at all. Later on this semester, we're going to be solving equations. Actually, it's in the very next section. I said later on the semester, but it's the very next section. That we'll want to make sure that maybe the equation involves a cosine of 2x and a sine of x. I'll want to use this equation to replace the sine of 2x, so I get rid of all the mentions of cosine. So that's the idea of why we care about these different particular formulations for the cosine of 2x. Are we okay with how we got those?
Yes.
No?
Yep.
Okay. All right. Well, let's see if it makes a little bit more sense, too, when we do some more problems here. All right. So let's look at a familiar type of problem that we've talked about this semester. So we're given some information about an angle. In this particular problem, we're given information about the location of the angle and, well, I should say the location of the terminal side of the angle and its cosecant. And then it asks you to find sine, cosine, and tangent of 2 alpha in all of these. All right. So first, let's look at this part. It says that alpha is between pi and 3 pi over 2. So what quadrant are we talking about if we're between pi and 3 pi over 2?
3.
Yeah, it's quadrant 3, right? So somewhere down in here, alpha would go all the way around this way. That's an alpha. That's whatever the heck that was. All right. So then we draw our reference triangle. We're given information about the cosecant. So what sides can we label when we're given the cosecant?
Hypotenuse.
Okay, cool. The hypotenuse and the
Opposite.
opposite. Cool. So what's the hypotenuse going to get labeled as? 17. Good. And the opposite side will be?
Negative 15.
Yeah, the negative 15. Cool. Good. Good. All right. So then we can find the adjacent side. If I call it, doesn't matter. I'll call it A. We can use Pythagorean Theorem, right? So we would have A squared plus negative 15 squared equals 17 squared. So we'd have A squared plus 225 equals 289. A squared is equal to 64. When we take the square root of both sides, we typically get plus or minus. In this case, do we want the plus 8 or the minus 8 for this particular triangle?
Minus 8.
Minus 8, good. Right? So that adjacent side, and the reason for this is the adjacent side is to the left of the y-axis. This looks like stuff we've done before, right? All right. Okay, cool. So the only new thing here is using our new formulas to help us out. Notice that we're only given information about cosecant of alpha. Our triangle is only in terms of alpha, not 2 alpha. So to be able to answer these, we need to use our new formulas that we just came up with to be able to rewrite these expressions. So what can we replace sine of 2 alpha with?
Sine of alpha plus... Wait, sine of alpha plus alpha.
Okay, so that was how we started the whole problem, right? Was when let me scroll back up here.
You just did did sine plus x.
So-
Sine x plus x.
So we did. That was how we started to get the formula, right? I just want to use our final answer that we boxed in here.
Oh, okay.
Yeah. So
2 sine x cosine x.
yeah. So we'll have the. So we can just rewrite this as 2 sine alpha cosine alpha. We could go through it like you had mentioned and doing alpha plus alpha and rewriting it. But that's kind of reinventing the wheel every time, right? We did that to start with to give us a formula that we can use, so we don't have to go back to that every single time. We can just use the formula that we boxed in at the end. All right. So notice here when we rewrote this, we got this in terms now of just sine of alpha and cosine of alpha. Can we use the triangle then to find these two values? What is sine of alpha in this case?
Negative 15 over 17.
Good. Negative 15 over 17, because that's going to be opposite over hypotenuse. And cosine of alpha will be?
Negative 8 over 17.
Good.
Yeah, it's hard to see how you got there.
Say that again? I just didn't hear you. I'm sorry. I thought there was a question. Sorry. We okay with that one? Yep. And again, just like before, I don't really care if you simplify this. You can just leave this like it is. All right. So cosine of 2 alpha, you get a choice because we had those 3 different identities for cosine of 2 alpha. So you get a choice for which ones you want to do here. One way to rewrite cosine of 2 alpha is cosine squared alpha minus sine squared alpha. Oops, that's a squared. That's one way to do it. And you just told me a minute ago that cosine of alpha was what?
Negative 8 over 17.
Okay, so negative 8 over 17, and that would be squared. And then sine of alpha was?
Negative 15 over 17.
Good. Squared. So that's one way to do it. And you could simplify that if you'd like. Again, I don't particularly care if you simplify it or not, but you could simplify that. Now, the other ways to have done this was what? What's another way to write cosine of 2 alpha? Using one of the other formulations that we have, what's another way to write cosine of 2 alpha?
1 minus cosine, or 1 minus sine 2 alpha.
So it would be 1 minus 2 sine squared alpha, that one?
Yeah.
So that would give you, we just said a minute ago that sine was negative 15 over 17 squared. And if you simplify both of these, you will get the same number. You can check it on your calculator if you'd like, but if you simplify both of these, you will get the exact same number. They both turn out to be the same thing. Or the third way you could have done this, the third way to write cosine of 2 alpha is 2 cosine squared alpha minus 1. And cosine was negative 8 over 17. And again, if you check this in your calculator, this number and this number and this number are all the same. You will get the same answer every time. Are there questions on that part at all? No? Okay. All right, so let's do the last one. Using our formula for tangent of 2 alpha, how can we rewrite tangent of 2 alpha? So 2 tangent alpha over what?
1 tangent squared alpha.
Good. Yeah, that's exactly right. 1 minus the tangent squared alpha on bottom. Good. And do we know what tangent of alpha is in this case?
Negative 15 over negative 8.
Good. Negative 15 over negative 8. So I'm just going to write it as 15 over 8 because the negatives will cancel. And then again, I don't care if you simplify that. Is that okay?
Yep.
These are the problems that you'll see on Hawks. These are the problems that Hawks has. They're all like this. They will give you, going back up to the top here of this problem, it will give you some information about one of the trig functions and then other information about where the angle is located, much like this one did. It will give you that information and then ask you to figure out sine or cosine or tangent of 2x or whatever. Now, usually when I give you these problems, I pick a nice Pythagorean triple to help to have you do it. If on Hawks, some of the problems will have a square root in there, and I would just leave it as the square root of whatever when you do it. Some of they tend to use problems that don't have necessarily the nice Pythagorean triples. But all right, any questions on any of those three at all? Okay. All right, so let's see if we can do one of these to verify some identities. Oops, I realized I made a typo. It should say verify the identity of sine of 2 theta is tangent of theta times 1. That doesn't look like a theta. This should say sine of 2 theta is equal to tangent of theta times 1 plus cosine of 2 theta. All right, so if we want to verify this identity, which side do you think we want to try to simplify, the left-hand side or the right-hand side?
Right.
Yeah, the right-hand side, right? It's a little bit more complicated here. So to do that, let's say we have tangent theta times 1 plus cosine of 2 theta. What do you think you might want to try to do first?
Can we change the tangent to sine to cosine?
Okay, we can change the tangent to sine over cosine. Good. And then, what do you think we should do with the cosine of 2 theta?
We can use the formula we just did.
Okay, yeah, we can use one of the formulas we just did. So maybe let's use the cosine squared theta minus the sine squared theta. Try one of them, see what happens. No, one of the reasons why I wanted to replace this one is because notice the tangent didn't have a 2 theta in it, right? It just has a single theta. So I wanted to get rid of this 2 theta to get single thetas to see what kind of simplifying we can do. I didn't want to leave a single theta and a 2 theta in there to try to do some simplifying. It's not going to work very well. So that's why I went ahead and replaced the cosine of 2 theta with the cosine squared theta minus sine squared theta. What do you think we
use the one that has the -1 in it, so that the 1 and the -1 will cancel out?
You could do that too. Absolutely. You could have used the 2 cosine squared theta minus 1. You could absolutely do it that way. If you want me to go ahead and do it that way instead? No? We'll leave it like this? All right. I'll leave it like this. That's fine. Because we could go ahead and distribute, but there is something else we could do, and this is what goes along with what Colin said. If you combine these two together, the 1 minus sine squared, what does that become?
Cosine squared.
That's cosine squared. Good. So I still have cosine squared here. Sorry?
You're making a lot of sense, but
Okay. All right. So then we have the 1 minus sine squared is cosine squared again. So how many cosine squareds do we have? We got 2 of them, right? Okay. So we got to the same place that Colin would have gotten to as well if it would have just started with the 2 cosine squared theta minus 1. And that was a good thought to do as well because, like Colin said, you noticed that the 1 and the minus 1 would have canceled right away. But we ended up in the same place, which is a good thing. We wanted to end up here anyway. What does this simplify to now? What can we do?
Just 2 sine theta, cosine theta.
Good, yeah. So this cosine theta will cancel out with one of those, right? And so you're left with 2 sine theta cosine theta. And now this, we should hopefully we start to recognize that this is sine of 2 theta. That was the new formula we came up with right at the beginning, right? So this is sine of 2 theta, which is where we wanted to end up.
Where did cosine go?
Where did the cosine go? So you've got a cosine in the denominator, and you've got a cosine squared over here. So I canceled one of the cosines. It's like canceling an x with an x squared, and it leaves an x. Same idea. You cancel that denominator out.
I'm still not getting it.
So you're okay to this point right here?
Yeah.
Where the arrow is? Okay. So what if I just had, say, I'm going to ignore the fact that it says cosine. I'm just going to write it as an x. If I had that, what would you do with the x's? Or the x's?
Cancel them out.
Yeah, so I'd cancel out, and it would just leave me with a 2x, right?
Right.
Right, so that's the same thing I did over here. I'm treating the cosine theta as that x. So I'm canceling out the cosine with one of the cosines. Or how about this way? That's what cosine squared means. Cosine squared means, right? It's cosine times cosine. And then one of them cancels out. So I'm left with the sine times the cosine.
Okay. That's that.
Other questions on that one? All right, so let's look at the second one here. Same idea. Which side do you think we want to work with?
The right.
The right? Good. I agree with that. Okay, so the reason I picked out this particular identity to work on is because we need to start thinking about this cosine 2x piece here. We need to start thinking about good things to plug in for it to be able to work on some of these problems. So notice that the left-hand side doesn't have a denominator, right? So if we're going to do this correctly, this denominator is going to have to cancel out. It's not going to have a choice. It's going to have to cancel out to be able to get to this on the right-hand side. Or excuse me, the left-hand side. So notice that the denominator does not have cosine in it at all, right? It only has a sine in it. So when I make a decision on what to plug in for cosine 2x here, I probably want to use the identity that doesn't have cosine in it. It only has sine. And the reason why I'm making that decision is because the denominator only has a sine in it. So when I go in here and plug in for cosine of 2x, I'm going to use the 1 minus 2 sine squared x. And again, the whole reason why I chose that one over the other two is because the denominator only has a sine of x in it. So I want to make the numerator only have a sine of x in it. That's not to say that if you would have used one of the other ones, you couldn't get to the same place. It's just a little bit faster if I go ahead and do it this way and eliminate any reference to cosine to start with. All right, so now on top, I get the 1 plus the 1 gives me 2. And I still have the 1 plus sine x on bottom. What does the two terms in the numerator have in common? What can I factor out?
2.
The 2? Okay. And this is another reason why I chose this particular problem for this identity, is because, again, coming up in the next section, we're going to be solving equations. One of the things that we're going to have to do with solving equations is factoring. Notice that this is a difference of two squares, right? I can think of this as 1 squared minus sine squared. So how does that factor?
1
Plus sine
minus.
x and 1 minus.
Yeah, so it'd be 1 plus sine of x, good, and 1 minus sine x. That's how a difference of squares factors, right? And now, once we've got that factored, what happens?
You can cancel off the 1 plus sine x's.
Good. And then we're just left with exactly what we want, right? That left-hand side. So this particular identity, why I wanted to do this particular identity to go through as an example, was not only to illustrate the cosine of 2x identity, but it was also to illustrate the idea of, okay, with cosine 2x, I want to make a choice as to which of the 3 formulations we have for cosine of 2x that I want to use. Remember that cosine of 2x, I've got 3 things I can plug in for it. I've got that cosine squared x minus sine squared x. I've got 2 cosine squared x minus 1. And I've got 1 minus 2 sine squared x. There's 3 different things that I can plug in for cosine 2x. The reason why, in this particular identity, why we chose the third one here is because I'm looking at the denominator. I'm keeping sight of what's going on in the problem. I don't see any cosines in the denominator at all. I also look at the left-hand side of the identity that I'm trying to verify. I don't see any cosines there either. So when I made the substitution for the cosine 2x, I used the third one here that had no cosines in it. I just got rid of all references to cosine to start with. So that was reason number 1 why I wanted to do this particular identity. It was to start to get used to that idea of, if I'm making a substitution for cosine 2x, what's the best one to make in the context of the problem? Had there been a cosine in the bottom, I would have used the cosine one. Does that make sense?
So are these things that you want us to memorize?
The things out here on the right?
Yeah.
Yeah, you need to know those. Absolutely. Yep. Okay, and so then reason number 2 why I wanted to go through this particular identity was this idea of being able to start looking at things and recognizing how to factor. Because this factoring stuff is going to pop up in the next section when we're solving these trig equations. And that becomes a very, very important thing to be able to do when you get to calculus, is being able to solve trig equations. All right, any other questions on that particular one? All right, well, let's look at what we refer to as the half-angle formulas. So there's going to be 2 of them we come up with. And this is actually, I'm going to go through these formulas and I'm going to stop today. The half-angle formula stuff is not in Hawks, which is why I'm going to stop here, and I'm going to spend more time on Wednesday going over more of these. But I just want to get you to where the formulas come from and talk about the formulas for a minute, and then I'm going to stop. I'll let you go look at Hawks on those problems. The Hawks homework's not due till Sunday anyway. I made it not due till Sunday, but the stuff that we've already talked about so far will get you through the Hawks homework with hopefully not too many issues. All right, so when we talk about what we mean by half-angle formulas, what we're talking about is we have formulas for cosine of 2x that reduce the argument here, or this inside of the cosine function, by a half. So all we're talking about with half-angle formulas is that we rearrange the formula for either sine or cosine so that the inside of the sine function is half of what's inside of here. So first, let's start with this one. So we'll start with this formulation for cosine of 2x. So we have cosine 2x is cosine squared minus 1. And what we're going to do here to change, this is one of the double angle formulas. To change it to a half angle formula, all we're going to do is solve for the cosine of x. So I'll add 1 to both sides. And then divide by 2. And then to get cosine by itself, I have to take the square root of both sides, right? Now, of course, we have to remember that when we take the square root, whenever you take the square root of both sides, you get a plus or a minus. Now, for our purposes, of course, when I plug in something for cosine x, I don't get 2 answers. So this is another thing that you have to make a choice on if you're using this particular formula. This plus or minus, this depends on what quadrant the angle is in. Whether or not you use the plus or use the minus depends on the quadrant. So what I mean by that is, if you had, say, 20 degrees, that would be in quadrant 1, so you would use the plus. If you had, say, 137 degrees, whatever that happens to be, that would be in quadrant 2, so you would use the minus. So the quadrant matters here for whether you use plus or minus. And when we do some examples, I'll emphasize that more. But just remember that it's not always a plus or a minus. You actually have to make a choice. Okay? You make a choice of plus or minus depending on what's on the inside of this thing. Okay? Now, it turns out that in calculus, it's actually this formulation that's more important. But what we're going to practice with are these here, or this one. All right, so this is the half angle formula for cosine. We can do a similar thing for sine. So restarting this, but using the double angle formula for cosine that involves sine, I use the 1 minus 2 sine squared x. And then I'm going to solve this for sine x like we just did a minute ago. So in this case, let's subtract the 1 from both sides. So I subtracted the 1 to the other side and then just wrote the equation in the other order since I'm trying to solve for sine of x. We'll divide by -2. And just to clean things up a little bit, I'm going to take the negative sign out of the denominator and run it through the numerator instead. So I have sine squared x is equal to 1 minus cosine 2x over 2. And then take the square root. And again, just like before, when we take the square root of both sides, we get plus or minus. And then again, just like before, this depends on the quadrant the angle is in. All right, so this is your double angle formula for sine. Notice that there's a lot of similarities between the double angle formula for sine and the half angle formula for sine and the half angle formula for cosine. Notice the only difference is the sign there in the middle. It's literally the only difference between the two. All right, like I said, we'll play with these more next time. I want you to get more used to the double angle formulas, but I wanted to get these written down so that we can just spend some time talking about when we know to use the plus and when we know to use the minus in the half angle formula. Okay, so the important part with these formulas is remembering what they are. I'm not going to make you rederive the formula every single time. So the ones that I have in the boxes are the ones that I want you to remember. But again, the idea with I want to play with this next time is I want to talk more and more about what this plus and what this minus means as far as what I mean by depends on the quadrant. Okay, so we're going to talk about that more next time. Does the idea of how I got to that point make sense as far as the derivation goes with just solving for cosine x or solving for sine x? Does that make sense to everybody?
Why are we able to, on the cosine 2x half angle formulas, why are we able to distribute the negative sign throughout the whole thing?
Down here, this one?
Yeah.
Okay, so all I did was I can think of that as -1 times 2, right? Okay, dividing by -1 and multiplying by -1 is the same thing. It does the same thing, right? And then I just distributed it to both terms in the numerator. I just moved the negative out of the denominator and pulled it up into the numerator and distributed it. I could have, instead of doing it that way, I could have started here. I could have taken the 2 sine squared x to the other side and subtracted the cosine first. Right? I could have moved this over here and moved this over here to get to here. And then divided by 2. I'd get to the same spot. Does that make sense? Is that okay?
Yeah.
Okay, cool. Any other questions on the derivation at all? Again, all we were doing was taking the original thing and solving for the piece that had just the x in it instead of the 2x. We okay with that for now? Let you digest it a little bit, maybe?
No, yeah, I'm straight.
Okay. All right. Okay. So, like I said, we'll do more of this Wednesday. I will be sending out a link for Zoom office hours for tomorrow. I'll definitely be on there at 11 tomorrow. And like I said, I'll send out a link for that. But if you need to talk to me some other time as well, just shoot me an email. We can schedule a time to meet if we need to talk or converse through email, any of those kinds of things. Also, if you don't mind, just send me an email of how you thought this went today, if I need to make adjustments and those kinds of things. I know it was just the first day, but I want to make sure that I'm getting the material to you as the best way that I can. And also, I recorded this, so I will get this posted on YouTube this afternoon so that you can watch it again if you need to. Are we okay for today?
Yep. Yes, sir.
Yeah, all right. Okay, well, at worst, I will talk to you all on Wednesday.